Hello, everyone. Today we're going to be going over Blueprint, which is a toolchain for highly reconfigurable microservices. So before we start, let's just get a definition of microservice. So traditional monoliths, you put everything on one server, and that obviously runs into some limits. And then you have distributed monoliths, where you put different components on different servers, but this tends to have problems with things becoming ossified over time, because everyone needs to use the same definitions of every single type, and the interface between components might be kind of flexible, which isn't always great if you need to integrate with a ton of things. So for the purposes of this, microservices are, I made a distributed monolith, but I have a solid API contract, and each service is implemented independently as a black box to all the other ones. Yeah. So the main problem that we have is there is a gigantic matrix of design decisions for microservices. So how you want to group the components, how do you want to scale the groups? Should groups go through a load balancer to talk to each other or talk directly? If these components are communicating, how should they communicate? Should they use JSON RPC, gRPC? Should they have a hand-rolled binary protocol? And traditionally, every single one of these decisions requires custom implementation, and that makes it so that evaluating different options is time-consuming and expensive. So what Blueprint does is it provides an abstraction layer, which allows you to easily move around components of your system and provide them with midware. So its primary goal is quick iteration over the many possible design decisions, such as, do we scale these together separately, or which RPC library do we use? It also allows you to have an army of developers focus on writing the business logic of your services, and then you can have a small group of experienced developers play with the design to optimize for performance, latency, fault tolerance, etc. So, of course, that is a fairly large claim, saying we solved the main problem of microservices. Oh, yes. So, question in chat. So the boats are monoliths. You put everything in one. You put all the services in one place, and then you have one service per boat for the microservice model. So Blueprint has two primary components. It has the workflow spec and the wiring spec. So this is admittedly a very simple service, but this is an entire service that fits on a slide, written in Go. So every service has to declare an interface, which I'm pretty sure is how the compiler determines what a service is. And then you make an implementation of that interface that has a constructor, and the constructor is how you declare your dependencies. Let's see if I can get a laser. Okay, can you see my mouse?
Yeah.
Yes, so you can see this requires a post storage service and a user service, and it's a compose post service. And Blueprint acts as a compiler, which picks all of that up and will check that you're providing the correct dependencies. And then this function here is the business logic area, which for this service is fairly trivial, but obviously might be larger in something real. The other half of this is how everything is wired together.
Owen, can you go back to the previous slide?
Yep.
Can you educate me a bit about the Go syntax and tell me more about what's going on here? Is that pointers and the star, is that all pointers or not?
Yes. It is a pointer, but it acts a lot like a reference type in Java or C#. And so this 1 to 3 here is an interface that requires you implement the compose post function. And in Go, interfaces are duck typed, so all you have to do is implement functions with the right signature, which this syntax here specifies on a compose post impl.
Okay.
So that's like the self or this parameter. This is the compose post function.
Got it. And other function, new compose post implementation, it's for initializing it?
Yeah, that's a constructor.
Yeah. Okay, cool. Awesome.
Yeah. So the other part of this is the wiring spec. And in order to provide abstractions for things that you might want to swap out, there's a bunch of built-in interfaces. So a cache interface is put with a key and a value and get with a key. And that's about as simple of a cache as you can have, but sometimes you don't really need more features than that. And that allows you to easily move between various types of cache. And then the other part is the wiring spec. And this is actual infrastructure, which I'm sure you've heard infrastructure as code before. However, a lot of times it turns into infrastructure as a way too large YAML file. And this is actual code. It's a Python file that they run through Python's parser, and then they extract some information from it. And they, in the paper, they claim it's a Go-inspired DSL, but they are just using a Python parser. Okay, so question. So they don't actually execute the code. They kind of execute it. Their compiler will choose sub-expressions to execute in order to do certain types of evaluation. Like you can declare a Python function in here and use that to abstract things, but any top level variable is expected to be some kind of wiring component. So the compiler is a little weird in that way. It's not how I personally would have done it, but I think that's something we can discuss later.
So, Owen, can you talk about the relation between the workflow spec and the wiring spec?
Yeah. So the workflow spec is essentially, this is the service at its most abstract level possible. You don't have to care about how networking works. You don't have to care about tracing or logging or other things like that. It's just, these are my dependencies, and this is the minimal interaction I need for the dependencies.
So at the workflow level, I write my business logic, and I hide all of these interactions behind the APIs that Blueprint has, right?
Yes. So then the wiring spec is essentially all of your ops concerns. So what are we deploying this application with? In this case, they're using Docker. Which RPC library are we using? Which normally isn't an ops concern, but Blueprint allows you to make it one. So they've chosen gRPC, and then you can have a tracing library. They chose Zipkin, and you can apply modifiers to it. So you might decide that you want to namespace your traces by, for instance, the system name or something like that. And you stack all of that up into something that describes how you make a server. And then the services that are needed. So there needs to be a memcached because there's a cache in front of the posts database. And then
How do we know there needs to be a cache? Was that mentioned in the previous slide?
So
Does
we don't
storage
see
service require the cache?
So the compose post service doesn't need a cache, but the post storage service needs a cache and a database.
Do we
So
see that in the signature in the previous slide? Did we see that?
no, we need a post storage service
Oh, okay.
here, and in this you can see it is composed of
Okay.
a cache and a database.
But if I'm not mistaken, Owen, can I, for example, make the cache nil?
Yes, so there is
work without the cache.
they have a quote unquote nil implementation of a lot of the interfaces, or null implementation. And what I believe that will do, in the case of, for instance, the post storage service, is it will mean just talk directly to the database.
So if I have that nil implementation of cache, essentially that's like composing that, microservice application without the cache, right?
Yeah. And although you see 2 calls to Mongo here, there's nothing that actually specifies those are partitioned. So the compiler looks at that and says, well, okay, I need a Mongo database, and both of these, the post service and the user service, both need to be able to talk to it. And if you want to partition things a little more, you do have to explicitly ask for that. That is an interesting design decision, which I think we can also talk about later. So then what you do here is you say, we're going to have a container, and we're going to put both the post storage and the post cache in that container, because by default, everything gets its own container. But you can choose to put multiple things in the same container for performance reasons, or because it doesn't make sense to ever not co-locate them. And then you can finally create the compose post service, and you have the server with the server modifiers. Yes, this is operating via dependency injection, Ruben. And this is it. This is all you need to define the service. And then they have a number of backends that you can use. The one that they recommend you play around with is Docker Compose. But they also have backends for Ansible and Kubernetes. So you can deploy bare metal if you want to. Or you can deploy in containers on top of a Kubernetes cluster. So currently, they do have a lot of categories of abstraction, but they don't always offer a lot of options. So for caches, they have memcached and Redis. They only offer MySQL as a relational DB. They use HashiCorp's console as a service registry, RabbitMQ as a queue, MongoDB for NoSQL. They do offer several tracing frameworks, and then 2 RPC frameworks. And then they offer an HTTP abstraction, but it's done in such a way that I don't think you would actually be able to slot anything else in there. And they also have various types of midware that you can use. For instance, circuit breakers, retry policies are controlled by the wiring spec as well. And then, as I mentioned before, deploys via Docker Compose, Ansible, Kubernetes. And this does have very substantial ease of use benefits. So if you look here for a bunch of fairly standard microservices, they're reducing the amount of code that you have to write in order to get something that functions the same way by about half an order of magnitude, which is, I think that is very interesting from the perspective of more flexibility and more and easier to implement. So another example of customization. This is the diff from, hold on, one of the Zoom bars is in the way. This is a get diff of moving something that was monolithic to microservices connected via gRPC, which in a normal application, that is a fairly substantial change, since when you have everything in the monolith configuration, which you can see down here, you can have it be process. You can put everything in there and it will just make function calls. And converting something that works like that into something that operates over gRPC with a diff this small, I think is very impressive. And there are no lines of code changed in any of the surfaces to support this at all. It is just this diff. Some of the other examples, turning off tracing required 418 lines of code in the actual implementation, and Blueprint needed 5 lines in the wire spec. And then swapping this gRPC implementation to Thrift at various configuration parameters, that is a 5 to 6 line change as well.
One question.
Yep.
Is this application or customization for an application that just involves generic components like database, caches, and the others that we have seen, or are there actually like a dozen business case specific microservices that they are also maybe changing?
So this does have a bunch of business specific microservices. So there's a post storage URL shortening, a mentions service, text and media serving timeline, user ID handling, social graph, home timelines again, a user login service, unique ID generator, and something to handle new posts. So there is a substantial amount of business logic in this, but you don't have to change any of it to completely overhaul how all of your services communicate. From stuff.
What we're changing here is the stuff that that the Blueprint was able to abstract away, right? Like network, caches, databases, those kinds of things, right?
Yeah.
So if I want to change something that's not hidden behind the Blueprint's abstractions, I'm out of luck, right?
Yes. Well, they also discussed this a bit, because one of their tests, they wanted to switch to a tracing framework which did not support the OpenTelemetry standard API. And it took them 200 something lines of code in the compiler and then 5 lines in the wire spec. But that involved bending the APIs around to make it work. If you want to swap from, say, MongoDB to DynamoDB, yeah, you're kind of out of luck. Like, you will still have to do some work there. But this does allow you to investigate compatible-ish solutions much more easily. So, for instance, RPC frameworks, which usually are fairly tightly bound to your application, this makes it easy to swap them out.
Does it allow you to swap out user business logic implementations, one implementation with another?
So I think the way you would do that is you would write another service that is similar, and you would plug that in.
Essentially, the user logic, right? The service logic is part of that workflow spec, right?
Yeah. Yeah, so you can't change the details of a service or what interface it provides, but you can change what dependencies you inject into it.
I see. Okay.
So one of the big places that this has an advantage for is if you want to do research. So this first graph here, what they did is they took one of the services in the hotel reservation system, and they added a 500 millisecond timeout to every single RPC. That was a one line of code change. And then they apply a high load, and of course it falls over. And because of the way the timeout works, you have amplification. And so this second one, they forced the GC to operate at only 75% full instead of 100 like it normally does. And then they caused some CPU contention, and that made the garbage collector thrash the system. And also a fairly large issue. And so this one here, I'm not sure how much Blueprint actually helps with that, but it does allow you to at least stand up existing services quickly in a way that you can investigate things like that.
Well, from the perspective of like metastable failures, right? At least we have like retry patterns or like caching, right? So those can be like all swappable components within the wiring spec, right? So you can try playing with different configurations of your retry strategies or different configurations of caches to maybe see the one that is more resilient, right? Towards some like triggers and whatnot.
Yes, one of the things they do later is they implemented circuit breakers, which was a grand total of 100 lines of code. And then they can just stick a circuit breaker anywhere that they want, or add it as a global modifier to all RPCs. And that they reran the type 1 experiment, this one, and it didn't have an issue. The circuit breaker kicked in and the service recovered quickly. So and what this allowed them to do was for instance, here they have the number of retries before you just declare something an error, and they were able to easily swap that out to figure out under how much load and for what duration of that load are these services vulnerable to falling over. And the ease of customization in Blueprint allowed them to go through this very quickly. And for anyone interested, the last one is just a very poorly timed cache flush. So one other example they had is this is the diff to move from a single instance of MongoDB to a replicated version of MongoDB. And with this, they were actually able to observe some anomalies as a result of the replication. I believe they weren't set up for wholly consistent replication, and they could see differences. So this also allows you to easily scale up databases, or scale them out. There's some features in there for placing particular surfaces on particular nodes if you want to be able to take advantage of vertical scaling by giving one service a really big system. But they set up replication, and then after their 10-ish lines of change to the wire spec, they were able to observe that no, their application couldn't properly handle the replication inconsistencies. And then they implemented something that will help handle that, which was another couple hundred lines. And I think most importantly for scientific use is it's really, really, really easy to add stuff to this. So these counts here are lines of code to add different implementations of interfaces. So, for instance, Redis took 140 lines in the compiler, and then to actually implement the thing that talks to Redis was another 76. And for these plugins,
when you say compiler, do you mean the Python compiler?
Yes. It reads the Python file and spits out additional Go code to generate the services. And the other thing that they have is plugins, which are sort of higher level concepts, like cache or relational database or deployer. So the retry plugin took 123 lines of code, and I believe it's implemented as midware for the RPCs. Normal tracing, about 300 lines. Replication, 52. So, and the circuit breaker, 126, load balancer, 208 lines in the compiler, 19 in the standard library. So in terms of effort required to have something that you can plug into the rest of the system, I think that this is incredibly valuable. Yeah, so Ruben in chat, at first glance, I thought this paper was about mutation testing at the infra level. I think it would be very good at that, because as long as you maintain the interfaces properly, you could just continuously swap things around.
It still has the feel of a research tool for me.
Yes, there are some rough edges. Getting the compiler actually functioning took me about an hour last night. Their ranges for dependency versions are not accurate. Very new versions of Python break the compiler because Python moved some stuff around internally in 3.11. But I think if some effort was put into industrialize this, there is a lot of promise in terms of allowing this to be used in industry to quickly stand up services and figure out how to plug them all together later. And then for scientific use, you implement your one thing as a plugin or a service, and then you stick it into this system, and you can evaluate it under something that anyone else can easily stand up with standardized workloads. And then when someone else wants to use what you wrote and build upon it, they can just pull in your service, make a couple changes to it, or use it as midware or an external dependency and do their work.
I think
So
prototyping is also important in industry, and like when you have many existing services like AWS, it would be useful to be able to show if we do this. I think the meta stability showcase was really convincing. You can show if we do it this way, we can avoid, we can be more robust, and then
Yeah, I handed this use case like really nicely by saying that it's so difficult to replicate metastable failures at small scale, and then like, we're gonna do it.
yeah. So there are a couple limitations right now. It is Go only. The authors claim adding more languages is just an implementation detail. I'm not entirely sure because of the way they implemented RPCs. I don't know if you could do it in a language that doesn't have runtime reflection. Because they want to send the type signature before you start doing any of the any of the data, which is how Go does RPC. And for C++ or Rust, that is very much not an option unless you want to bundle LLVM with your service. So it also requires that your entire system have one config file. That is not ideal for very large scale because it means that everyone will be touching the same config file. They said that they're working on that. And then the authors raised some concerns about the overhead of blueprints abstractions. When compared against other things implemented in Go, it's within a couple percentage points. But when compared against a system that was written in C++, there was a substantial loss in performance. Some of which can be attributed to Go is not C++. And they said some of it is likely because C++ is better at abstractions. Yeah. So, and that's the end of the presentation. We can move on to discussions.